This is chapter 5 and we will be discussing shear. This is the first session in shear and the 37th session overall. Here we'll give an introduction, discuss shear force and shear flow, and then shear stresses in beams. These are the topics covered in the first 4 chapters. They give the background for what we'll study now, that is shear. Shear and bending are inseparably linked, so notions developed in bending will be used in this chapter. This is the chapter on shear and will cover 6 sessions. We'll first look at structures with 2 axes of symmetry and then look at unsymmetric cases. Till now, we have dealt with bars subjected to axial loads, circular bars subjected to torque, and beams subjected to shear and bending. We have looked at internal forces. For beams subjected to shear force and moment, the internal forces were given in the form of shear force and bending moment diagrams. This is because often the shear force and the bending moment varied along the length of the beam. We have also looked at stresses in bars subjected to axial loads, circular bars subjected to torque, and beams subjected to moment. We have not looked at shear stresses due to shear force acting in beams. The stresses in circular bars subjected to torque and beams subjected to moment were found in a similar way. Thus, in both cases, the variation of strain in a section perpendicular to the axis was found first. Then Hooke's law was used to find the variation of stresses. The stresses were linked to internal forces. Thus, we obtained the torsion formula and the flexure formula. The variation of shear stress is found in a different way. Bending moment is inseparably linked with shear. Using the varying bending moment, we find the variation of shear stress. Here, first, the shear stress is discussed in a section with 2 axes of symmetry. We then deal with the case of 1 axis of symmetry and no axis of symmetry. We first discuss here a relationship between shear and moment, which was also obtained earlier. So consider this simply supported beam with arbitrary loading. We consider 2 sections 1, 1 and 2, 2, which are del x distance apart. This section is shown here with the loads acting. We assume that both the shear force and the moment acting are positive. Let us take a moment about this side of the section. There is a clockwise moment due to V, del x and m. The anti-clockwise moment is W into del x by 2 and m plus del m. Here m cancels out and we get this relation. Dividing both sides by del x, we get this expression. We let del x approach 0, so this second term becomes 0. V is given as dm by dx. We'll formally look at shear force and shear stress later on and derive suitable formulas. However, here we perceptually look at shear force, shear stresses, and strains in beams. Consider four planks placed on top of each other as shown and with supports on either end. Let us consider that a force P is acting. Then, after application of a load, we expect the planks to attain a shape such as shown here. The plank second from the bottom slides with respect to the plank at the bottom. Also, the plank third from the bottom slides with respect to the plank second from the bottom. The same happens with the topmost plank. In order that the planks do not slide against each other, we need to have the planks either glued or dowels attaching the planks to each other. In such a case, we can perceptually understand that there would be forces acting on the glue or on the dowels. So there would be shear forces acting between the planks, and as such, shear stresses acting between the planks. Now consider a cantilever beam as shown here with the force P acting. There are two sections 1-1 and 2-2. The shear force in both these sections will be the same. We consider elements of the portion to the right of 1-1. This is the expanded portion with the elements shown distorted. Since the shear forces on section 1-1 and 2-2 are the same, the shear stress at equal depth will also be the same. Since the shear stress is the same, the shear strength will be the same, and these two elements will distort so that their angles are the same. Here we have a cantilever beam subjected to a uniformly distributed load. One would note that the shear force in the section 1-1 and 2-2 will not be the same. Here again, in figure 6, this portion has been expanded. Again here, two elements which are shown shaded are taken at the same depth. However, since the shear force is not the same, the shear stress on these two elements will not be the same. Hence, the angle in these two elements will not be the same. Here we look at shear force. Consider a beam loaded as shown. There are reactions at A and B where there are supports. We take sections at 1-1 and 2-2 del x distance apart. The moment acting in section 1-1 and 2-2 are both negative. The moment in this portion will continually increase, so the moment in section 2-2 will be larger than the moment in section 1-1. The beam is considered to be made up of four planks placed on top of each other. Intermittent dowels connect the four planks. We consider that there is one dowel between sections 1-1 and 2-2, and it is shown in this cross section. The larger moment in section 2.2 is represented as m plus del m, while the moment in section 1.1 is represented by m. Due to the moment, these are the stresses acting. The magnitude of stress on the right side will be greater than the magnitude of the stresses in the left side. Because the moments are negative, the stresses above the neutral axis are taken as tensile. In this diagram, the portion above the neutral axis is shown. Now consider third section 3.3, which is taken horizontally. Let us consider equilibrium of this dark shaded portion. Since the stresses on the right side are larger than the stresses on the left side, the force acting on the right side overall will be larger than the force acting on the left side. So for equilibrium, the dowel will have to withstand a shear force. We earlier mentioned that the force on this side of this dark shaded portion will be greater than the force on this side. So the dowel must carry force. Here we have shown this dark shaded portion in 3 dimensions along with the dowel. The area on these two faces are the same, but the stresses on this side, sigma x2, is greater than sigma x1 on the other side. So the force Fx2 that acts on this side will be greater than the force Fx1 that acts on the opposite side. Due to this imbalance, there is a force del F acting, which the dowel resists. So we can write Fx2 minus Fx1 is equal to del F. Let this top surface be at a distance c from the neutral axis. And let the section 3.3 be at a distance y1 from the neutral axis. We consider the area of this thin element as dA. Then this equation can be written in this form using stresses. Now sigma x1 is equal to my by I, and sigma x2 is m plus del my by I. Substituting, we get this expression. Subtracting, we get del my by I to dA integration y1 to c is equal to del F. We have taken out del m by I outside the integration sign here. Now y dA integration y1 to c is the statical moment of this area. So we can write del F is equal to del m q divided by I, where q represents statical moment. The statical moment can also be given as yc, which is the distance of the centroid from the neutral axis into this area, as shown here. In the last slide, we discussed shear force in dowels. Here we'll discuss shear flow. We'll take the same loading case. So consider that the dimensions and the load, the reactions are the same as in the last case. Also, the moments in section 1.1 and 2.2 are the same. The moments are negative. The only difference is that this beam is a solid beam, so it is not made up of planks connected by dowels. So this is a solid section. As earlier discussed, the stresses on this side will be larger than the stresses on this side. Here we have shown portion of the beam along with the stresses above the neutral axis. As earlier, we considered a horizontal section 3.3. This shaded portion is shown in 3 dimensions here. We can consider a force Fx2 acting on the right side and a force Fx1 acting on the left side. These two forces are not equal, so for equilibrium there will be a force acting at the underside of section 3.3. Unlike the dowel taking this force, in this case the solid section will be subjected to this force. So we can write Fx2 minus Fx1 is equal to del F. Considering section 3.3 at a distance of y1 from the neutral axis and the top to be at a distance c from the neutral axis, we can write Fx2 and Fx1 by these expressions. We can write sigma x1 as my by I and sigma x2 as m plus del m y by I, and subtracting we get del m y by I into dA integration from y1 to c as del f. Now if this length is del x, then the force del F can be written as Q into del X, where Q is known as the shear flow. So this expression can be written as shear flow into del X is equal to del M into capital Q, which is the statical moment of the area, divided by I. With del X tending to 0, we get Q is equal to del dm by dx into Q divided by I. However, we earlier saw that dm by dx is equal to V. So we get equal to Q or shear flow is equal to VQ by I, where capital Q is the statical moment of the area. In the last slide, we discussed shear flow. Here we'll discuss shear stress. We'll be discussing the same problem as in the last slide. This unit Q gives the designation of the stresses. The stresses in this direction and this arrow at the bottom are designated tau yx. So the stress at the underside of section 3.3 would be tau yx. The shear flow was given earlier as VQ divided by I. The shear flow can be given as the shear stress in the underside into the thickness T. So we can write tau into T is VQ by I. This stress is tau yx, so it is given as VQ divided by IT. This section is also shown here. Let us consider that section 1.1 and section 2-2 are close to each other. So this section is only one element thick. Now shear stresses occur in couple of pairs. So for this element, if there's a shear stress at the underside, section 3-3, there will be shear stresses here on the other side and on the top. From the unit cube, we can see that the designation of this shear stress is tau xy. So even though the investigation was started in the horizontal direction, we have been able to find the shear stress in the vertical direction here. Since these two stresses are the same, tau yx is equal to tau xy here. So we can write tau xy is Vq by IT. Now this was the original loading diagram, and we can find the shear force acting on section 2-2. We have earlier given the internal shear force using shear force diagrams. So all these vertical shear stresses acting on section 2-2 will create that shear force. This element is shown here. So V here is the internal shear force acting at section 2-2. Tau xy is the stress, and the magnitude of the stresses will vary along the section depending upon Q. The shear stress at a given height is considered to be the same, with the maximum shear stress occurring at the neutral axis. In the earlier slide, we discussed tau yx and tau xy. In this slide, we'll discuss tau zx and tau xz. We consider the same loading pattern, but here we take an I section. Sections 1-1 and 2-2 are subjected to negative bending moment, and the bending moment in section 2-2 is larger than that of section 1-1. We have isolated the portion between the sections 1-1 and 2-2 as shown here. Then the stresses acting on the right side will be larger than the stresses acting on the left side. This time we take section 3-3 vertically at the flange as shown. The top of the flange of the portion is designated as ABCD. An enlarged version of this portion is shown here. This is section 1-1, this is section 2-2. The top here is ABCD, and this is section 3-3. Let the force acting on this side be Fx2 and the force acting on this side be Fx1. Then Fx2 is larger than Fx1. For equilibrium, a force del F must act on the section 3-3. So we get this expression. Now consider the underside of this flange to be at a distance y1 from the neutral axis, and the top of the flange to be at a distance c from the neutral axis. Then Fx2 and Fx1 can be written in this form. We can write these stresses in terms of moment, and we can use the relationship between moment and shear force to give the shear flow as Vq divided by I. This process has been carried out earlier. Here Q, the statical moment of area, is of CDEF. Q in this phase is given by shear stress into thickness. We'll now find the designation of the shear stress on this face. This is the unit cube. You can see that the stresses in this direction and the shaded arrow in the opposite portion of the cube is designated as tau Zx. So the shear stress that acting on this face will be tau Zx. The thickness here is the thickness of the flange. So we get tau Zx is equal to Vq by IPF. As earlier, we can consider the sections 1, 1 and 2, 2 to be quite close. This portion is again shown here. We consider this portion to be only one element thick. This shear stress is tau Zx and the direction is as shown. This element has two pairs of shear stresses. So the direction of shear stress on section 2, 2 will be as shown. On the unit cube, we can see that this direction and this shaded arrow is designated tau xz. So this shear stress is tau xz. Since in this element these two shear stresses are of equal magnitude, we can write tau xz is equal to Vq divided by I into the thickness of the flange. In this figure, this portion has been rotated, so we can give the direction of tau xz on section 1, 1. Here it was shown on section 2, 2. Here we find the variation of shear stress tau xy in a rectangular section. We earlier gave the expressions of tau xy and tau xz. Both these stresses occur perpendicular to the axis of the beam. We'll also find magnitude of the maximum shear stress in a rectangular section and the position of where this maximum shear stress occurs. We'll consider here a different loading compared to the last slides. So we have a simply supported beam subjected to a load P. We consider shear stress at the section CC. The moment acting on section CC will be positive. The section CC is shown here. We find the shear stress at AA, which is Y1 from the neutral axis. Tau xy is given by this formula. To find Q, we consider this thin element of area dA. Then Q is y dA, integration from y1 to h by 2. Now dA is b into dy, which has been written here. Integrating, we get tau xy as equal to v divided by I into y square by 2 with the limits y1 and h by 2, which gives us this expression tau xy. If y1 is equal to h by 2, then the shear stress becomes 0. So at this extreme edge, the shear stress is 0. From this expression, we can see that the variation of shear stress is parabolic. Also, the highest shear stress is when y1 is 0. So the highest shear stress is at the neutral axis. This is not the case in all geometries. For example, in a triangular section, the highest shear stress is not at the neutral axis. When y1 is 0, the maximum shear stress is given by this expression. So this is tau max. Using I is equal to ph cubed by 12 and the area as ph, we can give maximum shear stress as 3 by 2 V divided by A. We can show that the total shear stress acting is equal to the internal force P. Since this variation is parabolic, then the total force would be 2/3 of tau max into the area. So we get 2/3 into 3 by 2 V by A into area, which is V. We generally consider the shear stress to be constant along the width of the section. But in reality, the shear stress varies. For a square section, we find that the maximum shear stress is 12.6% above the average, and the minimum shear stress is 6% below the average.